Hello, this talk is for IEEE WASPA 2021. I'm Ryosuke Horiuchi from the University of Tokyo. This talk is about kernel learning for sound field estimation with L1 and L2 regularizations. In this research, I propose a method to enhance sound field estimation. What is sound field estimation? It is to estimate and interpolate acoustic field inside a target region from discrete microphone measurements. As depicted here, a target region omega is set where a number of microphones are located at position R. We suppose that sound sources exist outside of the target region omega, so sound wave arrives towards it. The observed signal at mth microphone, Sm, is modeled as this equation. URMK here is the pressure at the mth microphone with wave number K. Epsilon here is some noise. Hereafter, K is omitted for simplicity. There are mainly two typical methods for sound field estimation. The first approach is sparse or non-sparse linear regression, where sound field is decomposed into finite spatial Fourier basis functions, such as plane waves and spherical harmonics. The second approach is the kernel ridge regression, which is the extension to infinite dimensional basis functions. For instance, Ito et al. Proposed kernel interpolation of sound field. Let me describe the details of the method since our research is deeply related to it. The kernel interpolation of sound field is based on the kernel ridge regression using directionally weighted kernel. The estimation of the pressure field U in frequency domain is written as this optimization problem. The first term represents the squared loss between the observed signal and the sound pressure at mth microphone. The second term here is a regularization of sound field function U. The directionally weighted kernel associated with the reproducing kernel Hilbert space H is defined as follows. Here, S2 is a unit sphere, and Wx, called directional weighting function, is the weight for each direction. This is a definition of the univocal weighting function, Wx. Xi beta here is a normalizing constant to satisfy this constraint. As you can see, Wx has two parameters, beta and eta. Beta and eta are spread and the direction of the weighting respectively. The right figure is an example of Wx of two-dimensional when eta is in the positive direction of y-axis. As you can see, the closer it is to eta, the larger the weight becomes. The larger beta becomes, the sharper it becomes. So, how do you set these parameters? The previous work suggested that an appropriate setting of eta is the arrival direction of the source. Beta is a larger value as source is approximated more to a plane wave. With the kernel function, the pressure field U is obtained on the basis of the representer theorem as follows. And alpha here is defined as the equation, where S is the vector that is composed of the observed signal at each microphones. K here is the gram matrix whose element is the kernel function. It is experimentally confirmed by the previous study that this method can achieve high accuracy, but there are some drawbacks. Let me reiterate that the weighting function has the two parameters, beta and eta. Eta are empirically determined using prior information on source directions. In previous studies, however, the prior information on source directions for eta is not necessarily available. The appropriate setting of beta is not obvious, especially when the source is not a plane wave. Furthermore, appropriate parameter setting is more difficult when multiple sources and/or reverberation exist. So we propose a method to jointly optimize the weighting function according to the observed signals. This is formulated as the following optimization problem. Here, not only U, but also W are simultaneously optimized. How do you do that? Here are some ideas. Wx is represented as the convex combination of parameterized weighting function. And then weighting coefficients of the convex combination is obtained based on multiple kernel learning, or MKL, that is well known in the context of machine learning. Let me go into the details of these ideas. First, we discretize the parameters into d eta and d beta respectively, like this, and obtain d eta times d beta combination of them. Using the combination, Wx is represented as the convex combination of the unimodal weighting functions of different parameters. Then the kernel function is represented as weighting sum of subkernels. This is called multiple kernel learning, where optimal kernel combination weights are learned using training data. Some constraint should be imposed on gamma because excessively large gamma can lead to a small cost function. We considered L1 and L2 regularization. In the case of L1, the normalization is satisfied. On the other hand, L2 is relaxation of L1, which is experimentally confirmed that the convergence is much faster than that of L1. Let me give you the details of each case. In the case of L1, the optimization problem is written as follows. Here is L1 constraint, which promotes the sparsity of gamma, and this normalization is satisfied. This is reformulated as the follow. The partial derivative of J with respect to gamma is obtained explicitly. Then the reduced gradient method is applied to solve this problem. In the case of L2, the optimization problem is written as follows. Here's L2 constraint, which is a relaxation of L1 norm regularization. You can see that the blue line is a feasible region of L1, and the light blue region is that of L2. The algorithm to solve this problem is derived based on the minimax theorem for the dual problem, which is referred by Curtis et al. It is experimentally confirmed that the convergence of the L2 is much faster than L1 regularization-based algorithm. Let me describe the numerical experiment. The purpose of this is to compare the proposed method with the kernel interpolation without prior information, which corresponds to beta is equal to 0. 25 omnidirectional microphones were arranged based on T-design of 2 layers of the spherical surface, whose radii were 0.40 meter and 0.45 meters. It is conducted in 3D free field. 2-point sources are located. One is in the positive direction of x-axis. The other is in the positive direction of y-axis with some height. As for the parameters of the proposed method, d eta is set to 10. The zenith angle is fixed, and the azimuth are regularly divided between 0 and 2 pi. D beta is also set to 10. Beta is divided equally between 0 and 9. For an evaluation measure, we adopted normalized mean squared error, or NMSE, that is defined as this equation. This is the result, NMSEs. The horizontal axis is the frequencies, and the vertical axis is NMSEs. 15 frequencies from 100 to 1500 Hertz are investigated. The blue line corresponds to the fixed kernel function without prior information. The orange and the green lines are the proposed L1 and L2 method, respectively. As you can see, lower NMSEs were achieved by the 2 proposed methods, and L1 regularization performed better than L2 regularization at all frequencies. This is the pressure distribution and normalized error distribution on XY plane at 900 Hertz. The left here is a true pressure distribution. These 2 here in the middle are L1 regularization, whose NMSEs was minus 12.04 dB, and the other 2 on the right here are L2, whose NMSE was minus 8.82 dB. The normalized error distribution indicated that L1 can achieve low error at wider area than L2. This is also the result of the estimated value of gamma at 900 Hertz. The horizontal axis is beta, and the vertical axis is eta. The direction of 2-point sources approximately corresponds to eta is 0 here and 1.5 here. The gamma of L1 became sparse but large at only one source direction. On the other hand, the gamma of L2 became large at both of the source directions, here and here. Here is a conclusion. Thank you for your attention.